Dear friends, our Milky Way galaxy is filled with billions of stars and over 100 billion planets. Among these, there's a fascinating possibility that intelligent life forms might exist beyond Earth. This isn't just a fantasy, it's a question that science is trying to answer. Today, we'll explore the potential for intelligent life on other planets. Previously, we looked into the Fermi paradox, which is the contradiction between the high likelihood of extraterrestrial civilizations in the universe and the lack of evidence or contact with such civilizations. But now, we're shifting our focus. We're not just wondering if intelligent life exists out there, but also how we might overcome the vast cosmic distances to find it. We'll look at emerging technologies and theoretical pathways that could one day enable humans to travel across the stars. Imagine humans landing on a distant planet, becoming the aliens we've always wanted to discover. This idea is not just exciting, it changes our understanding of our place in the cosmos and highlights the significant first steps we're taking towards making interstellar travel a reality. Within our own solar system, the search for life beyond Earth is more practical. While the chance of finding intelligent life forms within our solar system may seem slim, there's hope of finding evidence of past or existing microbial life on nearby planets and moons. Mars, with its ancient river valleys and lake beds, has long been considered a potential home for life. But Mars isn't the only promising place. Jupiter's moon Europa is a particularly interesting candidate in the search for extraterrestrial life. This ice-covered moon is slightly smaller than Earth's moon and orbits Jupiter at a distance of approximately 628 million kilometers from Earth. Beneath its icy surface, Europa is believed to have a vast ocean of liquid water, possibly twice the volume of Earth's oceans, making it a prime target for astrobiological studies. The upcoming Europa Clipper mission aims to uncover Europa's secrets. Its main scientific goal is to determine whether Europa's subsurface ocean could offer habitable conditions for life. By conducting detailed reconnaissance of Europa's ice shell and underlying ocean, the mission seeks to assess the moon's habitability, studying its composition, geology, and the potential for water ice plumes that could offer direct samples of the ocean below. However, exploring Europa is fraught with challenges, including the moon's harsh radiation environment. This radiation can incapacitate or destroy a robotic lander within hours to days, even with robust shielding, making the prospect of human exploration with our current technology an elusive goal. With today's technology, a manned mission to Europa would be close to impossible, not only because of the vast distance but also due to the lethal radiation environment. This radiation would pose a certain lethal risk to any crew daring to venture to Europa. If exploring the potential for life even within our own solar system presents such an enormous challenge, how can we dare to imagine that we will one day explore the stars in our galaxy? There are two solutions for this. The first one involves designing and building what is called a generation starship. There's a hypothetical concept of an interstellar arc starship that travels at sublight speed. Such a ship might take hundreds to thousands of years to reach nearby stars. The original passengers of this generation ship would age and die, leaving their descendants to continue the journey. There are several issues with this idea. If the starship takes many generations to reach its destination, it's possible that more advanced technologies could be developed on Earth during the journey. These new technologies could potentially make the starship obsolete, or even enable faster spacecraft to reach the destination before the generation starship. This paradox raises questions about the feasibility and efficiency of generation starships. So, the second solution is to improve propulsion systems. NASA has hired Lockheed Martin to design, build, and test a nuclear-powered rocket for space travel. This technology could reduce a manned trip to Mars from the current 7-month minimum to as few as 45 days. A nuclear fission reactor would power the rocket's engine for nuclear propulsion. A nuclear propulsion rocket can theoretically achieve a maximum velocity of about 22 kilometers per s. However, there are designs that propose even higher velocities. For instance, a certain design using magnetic fields to channel hot gas out of the engine could theoretically reach speeds of up to 123,000 miles per hour, 197,950 kilometers per h, or close to 55 kilometers per s. But even with this speed that doesn't exist yet, it would take a nuclear propulsion rocket approximately 26,000 years to reach Alpha Centauri. The problem with space is that it's too vast. However, in the concept of nuclear pulse propulsion, it's suggested that a spacecraft could reach a velocity of approximately 13,411 kilometers per s, which is about 4.5% of the speed of light. This would theoretically allow a spacecraft to reach the neighboring star Alpha Centauri in 100 years. There are theoretical concepts for spaceships that could potentially reach speeds up to 10% the speed of light. One such concept is the use of solar sails. Another project, known as Breakthrough Starshot, aims to develop a nanospacecraft that could travel at 20% the speed of light. This project proposes using lasers to propel a tiny spacecraft to our nearest star system, Alpha Centauri. However, this concept faces challenges such as the survival of the spacecraft's electronics in the harsh conditions of space over a long duration. But for the moment, at least theoretically speaking, this project remains our best shot for reaching the stars. It is a project by the Breakthrough Initiatives to develop a proof-of-concept fleet of light-sail interstellar probes named Starship, to be capable of making the journey to the Alpha Centauri star system about 4.3 light-years away. A flyby mission has been proposed to Proxima Centauri b, an Earth-sized exoplanet in the habitable zone of its host star, Proxima Centauri, in the Alpha Centauri system. At a speed between 15% and 20% of the speed of light, it would take between 20 and 30 years to complete the journey, and approximately 4 years for a return message from the starship to Earth. The search for alien life is exciting, especially with the discovery of Proxima b, an exoplanet in the habitable zone where water might exist in liquid form. This discovery gives scientists hope that we might not have to travel far across the galaxy to find signs of life. However, it's unlikely that we'll find intelligent alien life on Proxima b, our first stop. So we look to Gliese 667cc, another interesting exoplanet in the search for extraterrestrial intelligence. This exoplanet is about 23.62 light-years away from Earth. With a theoretical spaceship traveling at 20% the speed of light, we could reach it in 118 years. Gliese 667cc is classified as a super-Earth, meaning it's larger in mass than Earth but smaller than the ice giants Uranus and Neptune. This classification is interesting because its position within its star's habitable zone suggests it could have liquid water on its surface, a key ingredient for life as we know it. The planet's intriguing characteristics make it a prime candidate in the search for extraterrestrial life, suggesting a world where conditions might be right for life to thrive, possibly even intelligent life under the right circumstances. Our next stop is TRAPPIST-1e, located about 40.7 light-years away from Earth. It would take more than 200 years to reach it with our theoretical spaceship traveling at 1/5 to the speed of light. TRAPPIST-1e orbits within the habitable zone of its ultra-cool dwarf star, where temperatures could allow for liquid water to exist on its surface, a crucial factor for life as we know it. This Earth-sized planet is part of a fascinating system where several planets have the potential for water. The prospect of alien life on TRAPPIST-1e is compelling due to its Earth-like qualities and the possibility of harboring water in liquid form, offering a tantalizing scenario for the existence of life. With its relatively close proximity and promising conditions, TRAPPIST-1e stands as a beacon in our quest to discover life beyond our solar system. Now we set our cosmic sail to Kepler 186f, an Earth-sized exoplanet orbiting within the habitable zone of the red dwarf star Kepler 186. It is located about 580 light-years from Earth in the constellation of Cygnus. It is so far away that if intelligent aliens had a hypothetical telescope pointed towards and piercing Earth's atmosphere, they would see the Earth in the year 1444, potentially witnessing the Americas before the Europeans did. This thought-provoking perspective underscores the vast distances and timescales involved in the cosmic arena. Kepler 186f's significance lies not just in its Earth-like size but in its position within its star's habitable zone, where conditions might be right for liquid water to exist on its surface, a crucial factor for life as we understand it. The planet orbits a type of star known for its longevity and stability, which could provide a consistent environment for the development of complex life forms should the right conditions exist. The vast distances to other planets pose a significant challenge for exploration and study, emphasizing the need for advancements in our observational technologies. Even with a hypothetical spaceship traveling at 20% the speed of light, it would take us 2,900 years to reach distant worlds. As we extend our journey through the galaxy, we come to Kepler 22b, an exoplanet located 640 light-years from Earth. This exoplanet, possibly larger than Earth, could potentially harbor life. It's located within the habitable zone of its star, suggesting it could have extensive atmospheres, vast oceans, or even life-supporting conditions. However, a journey to Kepler-22b, even with our hypothetical spaceship traveling at 20% the speed of light, would take an astonishing 3,200 years. These vast distances highlight the need for breakthroughs in space travel technology. Concepts like the Alcubierre drive, a speculative idea that proposes faster-than-light travel, offer intriguing possibilities. Although these technologies are purely theoretical for now, they spark our imagination about future exploration. We'll explore this topic and the potential for warping space to achieve faster-than-light travel in another video. Thanks for watching.